So I'm going to be recording the lectures for 7.2 and 7.3. One of the reasons for doing this is that for the week of 7.3, which is the week of the 27th of February, I'm not going to be here, and so you are required to watch my YouTube lectures for 7.3A and 7.3B. Do your work in class and turn the work in. So as a practice, what I thought I'd do is I'd do the same thing with 7.2. And so I have you kind of trained to do that while I'm here, so that you know what the expectations are when I go away. The other reason for doing that is that there is a movement beginning now about a different way of teaching, and I think it was partly inspired by Khan Academy. I'm pretty sure many of you have gone to their website to look at their videos. They're very decent, I'd say. So one of the things that's happening is that there's a different teaching methodology called inverted learning, where the students actually watch videos through YouTube or whatever mechanism the school decides to adopt at home, and then when they come into class, they're actually working on their homework, so that if they have problems doing the homework, the teacher's right there to help them out. So I'm kind of experimenting with that model here as well. So that's the other reason for doing this. So 7.2 is all about volumes of solids of revolution. And to see what that is, there's a website that I found that gives you a good dynamic interaction, or actually not an interaction, but a dynamic picture of really what's going on. So a solid of revolution, oops, where did this come from? I guess I didn't close it last time. If you take a look at this, okay, a solid of revolution is obtained by taking this planar area here that you see, okay, this planar area here, okay. So remember, a planar area is nothing more than an area in a plane, and if you then rotate this area about a line like that, okay, which is adjacent to one of the boundaries of the area. If you rotate it like this, for example, you get a solid that will look like this. Okay? And you can see, I mean, just looking at the picture, I'm sure Sam is going to see this right away. Real application for this. Okay? This kind of looks like a jet engine. Okay, looks like a jet engine. So obviously it'd be really nice to know what the volume of that beast is, because you want to know what the inflow for the jet would be. So real applications on this, okay? So let's see what really happens when you spin this area around, okay? And in the next clip here, you'll see how the solid is being generated by rotating this planar area here, okay? Right there, you can see it. Okay. See how as it's spinning around, you get actually a solid, and that's why it's called a solid of revolution, because that planar area is being revolved or rotated about an axis. Right. So 7.2 is all about doing calculus to find out these kind of volumes obtained by rotating a planar area, and there are several methods of doing this, okay, and so that's what 7.2 is all going to be about, 7.2 and 7.3, okay. In 7.2, we will use what's called a disk method, okay, disk method. In 7.3, we will be using, what was the other method called? The shell method, okay. And again, the reason for doing this is that if you take a look at your book on page 456, they'll show you all these solids that have been obtained by actually rotating some planar region about an axis, okay? And obviously you can see again that these are real life objects. Well, right here is a pill, okay? Well, why do you need to know the volume of a pill? Because you're going to have drugs in it, okay? You're going to have drugs in it, then you need to know how much you have, okay? Funnel, okay, well, you need to know the volume of the funnel. Well, you've got to know how fast things are going to be flowing through there, what the volume is going to be. So the applications are enormous, okay, and this is really a meaty chapter. Typically AP questions, a couple of free response AP questions out of this chapter. All right, what am I going to do? I am going to do examples. Okay, so before we do examples, I'm going to refresh from basic geometry from 8th grade or maybe kindergarten, what the volume of a thin cylinder, and the thin cylinder is also called a disk. Okay, so in this example here, you guys know that the volume of this disk or cylinder would be pi r squared h. Okay, pi r squared h. So that's just a review for kindergarten stuff, and now we actually do an example. Okay, so the example is find the volume of a solid of revolution obtained by rotating the planar region of the first quadrant of the circle x squared plus y squared equals 1 about the x-axis. Instructions. First, draw a diagram. And here's the diagram. Okay, so what we're going to do is we're going to rotate that yellow region about the x-axis. Okay, we're going to rotate this yellow region about this axis here. Okay, here is my representative rectangle. And as you can probably imagine that if I want to rotate this about an x-axis, I'm actually going to generate a cylinder. Okay, I'm actually going to generate a cylinder whose height is fx, okay, whose radius is going to be delta x. It's going to be delta x. Okay. Actually, take that back. The radius. So this would be the radius. Your cylinder will actually come out like so. Okay, as you rotate this around. So it's going to be a cylinder that's not going to be oriented like that, but it's going to be oriented the other way. Okay. So how do I draw this? It's going to be, well, I'm not going to try and draw that. You'll just have to imagine this. Okay, so the radius of the cylinder would be fx, its height would be delta x, and so from what we did earlier, the volume of the cylinder is pi r squared h, where r is the radius. Here's the radius of that disk that will be generated by rotating this about the x-axis. Here is the width. Okay, and then if you read your book, it'll tell you that, hey, if you want to find the volume of the entire solid obtained by rotating different rectangles, so you would pick another rectangle like so, rotate that, pick another one, rotate that, and then essentially what happens is that you're going to sum them up. Okay, so there is your Riemann sum kind of stuff coming along. So here's your fx quantity squared delta x, and you've learned that this then goes into becoming, if delta x becomes very small, like going towards 0, not equal to 0, but becoming close to 0, then this guy actually turns out to be an integral, okay, of pi fx quantity squared dx. So the summation becomes an integral, and then your limits of integration will be from 0 to whatever this x value here is, and if you look at the equation, that x value should be 1. Okay, so let's just go do that. Okay, let's go do this. So your volume would be equal to pi integral of this guy squared, so it'll be 1 minus x squared dx from 0 to 1. Okay, which then becomes pi, do the integration, and x cubed over 3 from 1 to 0, and this guy becomes pi 1 minus 1/3, which is equal to 2 pi over 3. Well, you can imagine that if you are rotating this yellow region about the x-axis, you're going to get a hemisphere. Okay, and the volume of a sphere, you remember from kindergarten, is 4 over 3 pi r cubed. the radius of that cylinder, that sphere is 1, so it'd be 4 over 3 pi. Okay, 1 cubed, so that's just 4 over 3 pi. And the volume of half a sphere would be half of this, which is 2 over 3 pi. And lo and behold, that's actually what we derived. Okay. So this topic really, you can kind of relate to where these formulas came from. Okay, where they came from. They came from calculus. They came from calculus. All right, so one example down, many more to go. Next example, well, you're not here, so I guess I get to do it. And the same kind of thing, that except that instead of the radius being 1, it is r squared. And let's go do this. Okay, so I'm going to go, well, let's do this from scratch, and so you guys get an idea as to what needs to be done. Okay, so first things first, you need to graph this. So you know that find the volume of solid obtained by rotating the plane region of the first quadrant of the circle. Okay, so here's my x, here's my y. My circle kinda looks like this. Okay, where this is r, that's the radius, and that is r as well. And it's telling you that you want to rotate this planar region here. Okay, all this region here about the x-axis. So let's start doing our representative rectangle. So here's my representative rectangle. Okay, so again, imagine rotating this about the x-axis. Okay, rotating it about the x-axis. You're going to generate a cylinder or a disk whose height is going to be fx, whose radius is fx, whose height is delta x, and you're going to integrate. Okay, and the volume is going to be, so the representative volume is going to be pi quantity fx quantity squared dx. You're going to integrate this from 0 to r, and you're just going to do it. Okay, so remember that from here y is equal to square root of r squared minus x squared. Okay, so doing the integration, you get pi integral 0 to r of r squared minus x squared dx, which gives you pi r squared x minus x cubed over 3 r to 0, which is equal to pi r cubed minus r cubed over 3, which gives me 2 over 3 pi r cubed. And just like in the previous example, you realize that's the area of a hemisphere. Okay, so you can see that if you were to rotate this yellow region, that's what you'd actually get, a hemisphere. So the idea makes sense. So the things you need to do are, first of all, graph the equation, create a representative rectangle, hence a representative volume. Okay, write that as an integral, and then just do it. So this is actually called volume of a solid of revolution using the disk method. Okay, using the disk method. And what we have is a representative disk generated by this representative rectangle. And notice that in this method, the representative rectangle is at right angles to the angle to the axis of rotation. So here, the axis of rotation is the x-axis. So your representative rectangle is going to be vertical. Okay, it's going to be at right angles to it. In 7.3, we do the shell method, where the representative volume of the rectangle is going to be parallel to the axis of rotation. So that'll be a different technique. Okay, different technique. Okay. Example 2 down. Example 3, I do again. So find the volume of a solid of revolution obtained by rotating the planar region formed by the graph of square root of sine x in the x-axis in the interval 0 to pi about the x-axis. Draw a diagram, write the volume as an integral, and just do it. Okay, so let's see what the diagram looks like.